Log on, tune in, find out. Another good idea from Cambridge.
By Bart Preneel on theory and practice for hash functions.
Thanks for all coming back. There is 3 difficult things in life. Climbing a mountain that leans forward, kissing a person that leans backward, and giving a talk after lunch. So I'll do the third thing. So I'll hope to entertain you about theory and practice for hash functions. It's actually the easiest object we have in cryptography because there is no keys. So just take any message, any size. You have an efficient algorithm to reduce it to a short string, and that's it. How simple can it be? Of course, those of you who know about the hash function wars and crisis know that we've been shifting generations, and we're now looking forward to SHA-3. So what I'll try to do in this talk is give you a little bit idea what's happening in practice, but also what's happening on the theory side, and try to see whether we have a link between those two. So essentially, of course, hash functions are used everywhere. I try to pay attention. There were great talks so far, and I think all speakers have at least used once the word hash function. So it's actually used everywhere, and I guess you know all the uses. A short unique identifier to a string, as for example used in signatures, or in the new cryptographic protocol in data authentication. It's actually a protocol which was used in Kerberos before. For one-way functions, confirmation of knowledge and commitment. You heard Hugo's talk about entropy extraction and pseudorandom string generation, key derivation. And then also for some crazy reason, about 20 years ago, we started building everything based on hash functions. Even other primitives you can perfectly do without hash functions. And so when the hash function crisis came about, 2004 or 5, Microsoft was looking around and they found 800 users of MD5 in Microsoft Windows, so they hired the MD5 removal person, who is probably now the SHA-1 removal person. And I think this person may have a long career ahead. So essentially in this talk I wanted to look at theory and practice and see whether we can actually make a bridge between those two. And so whether theory can help us to get better hash functions and deal with this crisis. I have a lot of slides about definitions because this is where a lot of theory work has been done. I don't really intend to spend too much time on them, so we're going to rather quickly over them. But I try to give you a flavor, and the main message is, even if the object is very simple, definitions or defining what it is and what we need seems to be very hard. There is plenty of PhD theses to be written on that topic still, I think. So I guess the easy things you know. So I found in the thesis of Merkel a long time ago, pre-image resistance, second pre-image resistance, and collision resistance. And these are the 3 main properties a hash function has to satisfy. Of course, we realize there is more things, and the first thing that came up, I think, was discovered when people in the IETF tried to make a Mac based on a hash function, and then they figured out that actually if you stick a key in the beginning, then you're vulnerable to length extension, because we have iterated functions. Even if you don't know the key, or you don't even know x1, x2, x3, if you know the result, you can actually easily extend the message and send the computation, which is definitely not something you can do for any random function. And of course the fix is known, it was just never applied. Already in the early 80s, all our Mac algorithms had an output transformation. We knew how to do it, but for hash functions we somehow didn't do this. And of course it was neatly formalized, and I think it kind of solved that problem easily. So if you look at the NIST requirements for SHA-3, you find some other things. So since the length extension has been added, then properties scale well with truncation. So if you use, say, only 50 bits, you should still get like collision resistance 2 to the 25, something like this. HMAC, so your hash function has to work in an HMAC mode. If it doesn't, you have to make sure it somehow does. It has to be indistinguishable up to 2 to the n over 2 queries. And then you also want security in randomized hashing mode, and I'll come back to that. This part of definition NIST already had to change after a few months. There was actually on the website an update to what was published in the official register. They only had 2 years time to think about this call, so it was clearly they were not ready to figure out what they really needed. So something we often overlook in crypto, and I will not come back to it, but I think it's very important if you move crypto from theory to practice. In practice, hopefully you're successful, and there is not one instance of your problem, but there is m, where m is a large number. And so many proofs only apply when you actually use a system only once. And of course, the opponent has two settings. Either he wants to solve one of the problems, like breaking into one of the bank accounts and get rich. And if you have 2 to the t targets, you gain a factor 2 to the t, for example, on per-image attacks. Or you have more the, I would say, an NSA trying to get keys approach, where you want to solve all the problems. And then we have time-memory trade-offs. But so even for per-image resistance, the easy problem, we say we have n-bit security, but in real life, if you have many targets, you have much less security. And if you have an m out of m thing, you have, of course, a one-time 2 to the n effort, but then the marginal cost to break one is about, the most extreme case, the 2n over 5. Of course, this is very extreme. I think the 2 to the 2n over 3 is more practical. Of course, we know an answer. It's already the thesis of Merkle. This guy really did amazing things. So the answer is randomize your hash function, use a salt, use a key, use a spice, or whatever. It's something cryptographers love to do. You have a problem, you shift it somewhere else. Because the question is now, who will manage this? Who will choose this? And how will I integrate it into my API? So if you want to formally define this, I'm going to very quick. It's a good exercise for a student. It has first been done asymptotically. Of course, now we have concrete security definitions. But essentially, if you read the literature, you know how to do this. It's not very difficult, how to formalize pre-image resistance. But you have choices to be made. For example, I wrote here, let X be selected uniformly in the domain. But nothing stops you from choosing Y uniformly in the range, or maybe according to a weird distribution in the range. Or maybe your X has a weird distribution. And then again, you get a different definition. Second pre-image resistance, similar. So same issues, but it's actually all trivial. Although it took a very long time before this ever was written down. I think it was kind of known it could be done, because actually the first time these definitions were written down was for collision resistance. That was felt to be more important, and so this is the work of Even Damgaard. He was the first one to formalize this, 87. And if you take the same approach, of course, it's very simple. You consider a hash function. For each collision string finder, uses time at most t. You either output question mark or a colliding pair. And so the probability of this machine over its coin flips should be at most, that is a question, not a question mark, so you get the collision is at most epsilon. Does it work? I guess there is many people here know, of course, it doesn't work. This is not correct, because you require for each collision string finder that it's not possible. But of course, we know for any fixed hash function, there are collisions. And so you can imagine easily that such a machine exists. We just don't know how it looks as stupid humans. But smart humans may know how it looks, or smart machines may know how it looks. And so you can't say there doesn't exist such a machine. So it's a kind of problem of the formalism. There is two ways around it. The solution by Damgaard is to have a family of functions. So again, you have this parameter, the same as Merkle did, and it's called a key. Index of the family. It's a public thing, it's not a secret thing. And so now the machine actually gets on input a key and has to produce a collision. And so if the space of these keys is large enough, you can never store in one machine collisions for every member of the family. So kind of the problem is solved in theory. Of course, in practice, the question again, where do we get this solved from, or this key from? So there is another solution, very neat. It was observed by Stinson, but Phil Rogway wrote a very neat paper about it. You can actually use this concept of no human can find the collisions and use it in reduction proofs. May look a bit weird to real mathematicians. They say these cryptographers are really a bit crazy. But in fact, you could use this statement saying you can either break this protocol or a human exists that can find the collision. That's what you can prove. And then the other implication is, this is nice work by Phil Rogaway and Tom Shrimpton in 2004. Of course, if you have a parameter anyway, you can as well now look at the definition of second pre-image and pre-image resistance. But now you have many choices. So you have now second pre-image and pre-image resistance for a family rather than for one function. And so now you can actually choose both at random in your experiment, in your game, or you can have a random algorithm with a fixed challenge to invert, for example, or you can have a fixed function and a random challenge. And so this is the ESEC and EPRI and APRI and ASEC variants. So this is very neat, and you can start studying this, and did very nice work about this. So there is a dotted arrow if there is an implication under certain conditions, there is a full arrow if there is an implication, and there is no arrow if there is a separation. And then Lena Andreeva and Martijn Stam actually generalized the definitions a bit, and I think there were also some small changes proposed, but they also looked at range per image resistance, where the element is chosen in the range, and domain per image resistance. And so there is more results. This is quite recent work. But so, in theory, it's very easy to prove COL and ESEC, but what we're really interested in is actually domain-based pre-image resistance. And this seems to be harder to automate. But in general, we have good news. So collision resistance implies a lot. This is the good news under certain conditions. What is the bad news is that you can only get a security bound to the n/2. Because normally, at least if you have a single pipe, a narrow pipe hash function, you only get security bound to the n/2. If you transfer the same proof to per-image resistance, you don't get the full per-image resistance. So it may not be good enough, not good enough for NIST in any case, because NIST wants to do the n secured. So collision resistance seems to be more complex to formalize. There is theoretical results, a very nice paper by Dan Simon showing that it may be also theoretically harder. And as we know, most attacks on hash functions find collisions. Very few find per-images or second per-images. So it seems to be also hard in practice. And so this is the reason for the hash function crisis. There is some good news because most applications, or it's not always necessary to have collision resistance. There is even better news. It's rarely necessary to have collision resistance. And this is what SAFES does, because we have a primitive like MD5, which is massively used, which is now broken in microseconds. And still everybody has time to go to conferences. So there must actually be not such a big problem, right? Because I haven't seen a decline in attendance for crypto and Eurocrypt in the past 5 years, so there must be no really big crisis. So, of course, how can we get rid of this? So this was the main reaction. We don't really need it. But maybe somebody here has an application where they need it. Maybe that's a question I should ask. Somebody needs collision resistance in the application? Nobody has one? Who has signed the document ever? Nobody. You see, there is no problem, in fact. Like, we can skip this talk at all. So, of course, we have a very neat theoretical solution, which is you first send a message to the signer, who has a secret key. Then the signer chooses at random a key. And then he will actually sign the hash of the message, where the hash is chosen from this set. So it's a keyed family of function, but it's an unkeyed parameter, a public parameter. And you probably also sign R with it. This kind of solves the problem, because now if you have collisions, what can you do with them? Right? The signer or anybody else could produce collisions, but you don't know what hash function will be applied in the signing process. So it's very unlikely it will be useful. So this was first formalized in '89 by Naur and Jung, and they observed that this is easier to get than collision resistance. So it works in theory, essentially explained in words here. So you can no longer use collisions, and this object has been given now at least 3 terms: roofs, target collision resistance, and also ESEC. So does it work in practice? So in the theory, the problem is fully solved. I agree to this. In practice, for example, we can read in the newspaper what happened in 2005. So somebody in Australia is far enough away, nobody can really check this, got actually a fine, a speeding fine. And so interesting that a government agency failed to prove in court that the algorithm was cryptographically sound. So it's really amazing. We should stop our work. It's actually the lawyers who prove our algorithm sound, right? And so I'm actually wondering which lawyer can prove in court the cryptographic algorithm is sound. On the other hand, what the blogger writes is those attacks remain largely impractical. This was the common belief in 2005. I guess he may have changed his mind now. So what is the problem with this scheme, or I see as a practical problem? What if the signer attacks? So the signer first chooses the random, then finds collisions, which may be easy here, and then signs one message, and if there is a dispute, he signs the other message. The theory gives a very clear answer. You're responsible for everything you've signed. You signed M and M prime, you produced collision, that's your problem. The real problem is, how will you explain this to a judge? That there is a difference, right? And so of course, I would say as a lawyer, NSA has found a second pre-image attack on this hash function. It's not me who did collisions. and then you need 10 years to train the lawyers to understand the difference between the two, and maybe then it will be solved. But so, it's not so easy in practice, I think. We have to random properties for hash functions. I know you're going to react, but I'm first.
Even that no one uses signature, why do you care?
Yes, exactly.
No, and also, I don't think that it's much harder to educate them to that case than to educate to any case of believing in this notion of collision resistance. Or
Well, I think, at least in this case, we have an example of a judge who doesn't understand it, right? So you maybe should go to Australia and educate this judge, and then you can
I
change this
don't
judge.
think that you have to build on this example to.
Well, I think it's actually what I expected would happen, what also happened. Okay, I think we should take this offline because I knew Hugo was going to disagree heavily, so that's okay. I discussed it with him before. So we have the randomness. I guess you all know this game, so I don't have to say too much. But it doesn't work for a hash function because we have no secret key, and so there was no way how to formalize this. So this actually was then solved by looking at the indifferentiability model by Maurer and his colleagues, and so by Coron was applied to hash functions. So essentially, what you have a game where you have the hash function using an ideal object, a fixed input length quantum oracle, is to compare it to a variable input length quantum oracle that actually calls a simulator. And so if you can construct it a simulator, you can't tell the hash function using the ideal building block apart from the real random oracle. And this, of course, if you satisfy this property, you have no problem with length extension attacks. What is the bad news? Last Eurocrypt, our session chair, together with some other people in the room here, showed that for some applications, actually, it doesn't even work. So you may have differentiability, but you don't get the security you need for the application, which is very disappointing. So this shows gaps in the theory. We may need other properties, like near collision resistance, partial per image resistance, chosen prefix, second per image resistance. I mean, I could fill slides and slides with new things, but which properties are really relevant? And maybe for every application you have to study in detail what you need. So we just did work on a few properties, and there is some relations known, but if you look at all the other properties, you can start formalizing them and seeing which implies which. This is all the thesis to be written. Should we now have a keyed or unkeyed function? Because SHA-3 will be a fixed function, right? To my understanding, you may have a keyed function, but my understanding is that if you submit or if you have a keyed, for example, Johan Dahmen from Ketchak believes that if you need to key the function, you put any salt so anywhere in the method and it works. So SHA-3 may still be a fixed function, in spite of all the theory. And then, of course, the real question is who chooses the key? And, or is it a salt? And is the salt the same as the key? And you can have interesting discussions about this. So I guess my conclusion to this part is it's a bit foggy with the definitions. We understand much more than, I guess, 10, 15 years ago. There was in fact, the attacks, very interesting, the cryptographic attacks on MD5 have resulted in a very big boost of the theory community writing lots of papers about hash functions. But then strange enough, with a few exceptions sitting, most of them in the room, after SHA-3 started, the theory community moved to something else. So when it really started mattering, they actually disappeared and we're no longer interested in the problem. It was the hype of 2005, 2006. But I'm not sure we can solve these problems anyway, but it's interesting to observe. There's a hype cycle in research. And so it's a very short burst of interest, and then there is no interest anymore anyway. So how do you make a secure function? So by iterating a compression function, this is what Rabin did in 1977, using DES to make a hash function. And then in 1989, we got these two theorems at crypto, essentially saying that a collision resistant compression function is sufficient to get a collision resistant hash function. So you can actually prove a property of a simple building block and build something larger. For this, we need to fix the IV. And this is actually a great achievement of these theorems, because until 1989, people never specified their IV with their hash function. So this is, I think, a clear example of where theory has helped, because the theory it was necessary to fix the IV, or at least have a suffix-free encoding and the IV and the padding and so on, the whole thing. What the theory showed was actually applied in practice for the first time, I believe, in MD4. So this is an easy result. On the other thing, which is still completely unresolved, most of the results on hash functions look at the compression function as something taking one input and compressing it. While in real constructions, you have two inputs, an HI, which comes from the previous stage, and an X chosen by the attacker. So if you look at all the SHA-3 designs, or in the final, they all treat X in a different way as HI minus 1. But I still haven't seen any theorem, or very few theorems, that treat hi minus 1 and xi differently. Right? They actually treat it more or less the same. There is some exceptions, but more or less is being ignored that there is actually two inputs. There is kind of a discrepancy between the theory, I think, there and the constructions. So then, of course, we also learned that there is quite some problems with this Merkle-Damgard construction. There is a multi-collision attack, a very cool attack. There is a long message attack, which actually shows that if you find second pair images for longer messages, it goes a lot faster. And then there is the herding attack, which has to do with commitments. So essentially, the main message from those attacks is that even if we like Merkle-Damgard and it's being applied in all our hash functions, and even if it preserves collision resistance, there is actually many problems with it. I think that's the main message which we discovered between 2004 and 2006. So there was also some cryptographic work around this time. So I'll show you some other constructions, but SHA-3 may look more like this. So you have now a double internal state. Some designers prefer to do this to have no problems with multi-collision attacks. On the other hand, you pay a performance price for this. And NIST has required that SHA-3 be faster than SHA-2, which I think is completely crazy. And I think they're coming back a bit from this, because in fact there is no SHA-3 candidate faster than SHA-2 on all machines. It doesn't even exist even today in the finalists. But so you may have a larger state. You may have a counter to defeat these long message second pair image attacks. Of course, you have an output transformation to defeat length extension attacks. That's more or less it. So we have now, I think, a better understanding of why to build a different structure and why to do certain things differently. And this is explained on this slide here. So, but people have been trying to do things and don't try to decipher all the details, but I found at least 12 constructions which are older, but have been studied, and to see whether they preserve actually any of the properties. So there is actually 8 properties, which is collision resistance, 3 variants of second per image, 3 of per image resistance, and the indifferentiability property, whether they preserve them. And you see, in fact, most constructions don't preserve them. This is something we did a while ago. It preserves it. It kind of needs a random oracle in the construction, so it's kind of a little bit of cheating, I must admit. It's not a standard model, full standard model proof. But so you see many gaps. It's very difficult to make something or find a construction that preserves everything. So collision resistance is easy. ESEC is not too hard. EPRE is not too hard. And then indifferentiability we also know how to do now. By now we know it. But all the rest we don't preserve. And anyway, no cryptanalyst tries to find second pair images for compression functions. It's very rare to try to do this. They try to find non-randomness for compression functions, whatever that means. So few constructions preserve properties, and there is still open problems, and you can still make different iterations that have different preservation properties. There is also now quite some constructions known where the compression function is insecure, but there is a quite complex proof for the security of iteration. So do we want this? So we don't want a simple building block we understand. We just say the big thing is secure, and here's the proof that tells you why. So Merkle-Damgard also, there was a very nice work pointing out that we can make it PRO, so pseudo-random oracle property, or indifferentiable, if the building block is per image aware, which is a weaker property than being PRO, but of course it's very hard to test in practice anyway for any function, I think. So many of these reductions are in the ideal model, make very strong assumptions about the building blocks. I will come back to that. Some of these reductions are not very tight. And so another question I keep asking is, does it really make sense to preserve per image resistance? Because if you XOR all the input blocks and then you put a one-way function, it's per image resistance the result. In fact, why do you need to have per image resistance in the iteration? Because it doesn't you can have a secure function which is completely insecure in the iteration and still is per image resistant. So this is interesting observations where there may be improvements to make. So next, how to build compression functions. So we're going to dive inside. So essentially, what people did was look at block ciphers, because that was around in the 80s. People built hash functions based on DES and then on AES, although I guess the weaknesses of DES, the sizes of the parameters are too small, and AES has now some key schedule weaknesses which make it very unsuitable for these constructions. But essentially these constructions are very well understood now. So we know if you have a block cipher, how to make a hash function if the block cipher is ideal. We still don't know how to make an ideal block cipher. So, and any small deviation might be dramatic for the result, but still what you see for SHA-3 is people build large block ciphers. And then they use this kind of modes. So Blake, this is an what? So I think Skane is in this case. Skane has this approach, has a large block cipher and one of those modes or a variant of it. Blake is slightly different. It's kind of Davis-Meyer, but it kind of doubles the state internally and then reduces it again. But note, for example, that Blake treats hi minus 1 xi differently. One is a key and the other one is a message style input. And then Johan Damen and his colleagues build on earlier work of Johan Damen from the early 90s to actually not build a hash function based on a compression function or a block cipher, but based on a random permutation. It's a very fresh idea. You need a much larger state, so you catch like 1600 bits, and they call it a sponge because you actually absorb the message, and then in the end you squeeze it out, and in fact you can make any length of hash result because you can keep squeezing your sponge and get also, for example, a hash function with a 3702 bit result, which is kind of neat. So there have been quite some designs following this model. The beginner designs had a buffer to protect a bit the squeezing phase, but somehow this has been dropped, and the view is now that, well, you should actually have a stronger permutation so you can drop the buffer. And then, together with some of my people in Leuven, we actually generalized this construction so that many SHA-3 candidates fall under generalization of sponge. We call this parazoa, which is kind of some biology here. So sponges are part of these classes of animals, and so we actually showed security properties if the permutation pi is an ideal permutation, which of course it's not. But this is the assumption, which is maybe a weaker or easier to verify or easier to get assumption than a block cipher is an ideal cipher. It may be more easy to believe it. So GH from Hongjung Wu actually has a large permutation and a very strange and interesting mode, which has very nice properties. And then Grössel has two permutations as well. But then Grössel by itself, you can see this as a block cipher in kind of DESX style mode. So it's Grössel has the two. So there is now a lot of understanding. I think there has been quite some study of those things, what we can prove about them. And there is also, this work has inspired study of older things, like if you look at the IBM hardware modules, they probably have the old hash function from IBM, MBC2 and MBC4, which are actually based on DES. And are kind of the best known ways, at least 20 years ago, to make a secure hash function based on that. So there has been a very nice result by Steinberg at Eurocrypt 2007 to actually prove a lower bound for collisions to the 3n/5. And so my student, Bart Preneel, has recently also is the first one to prove bounds for MDC4. So you can actually prove now that MDC4 is really faster than, and it's more secure than MDC2, it's 2 times slower. If you make the assumption more relaxed and you allow for a double size key, which means you make a stronger assumption, but an ideal cipher, then actually there is several constructions which have better security. But you have already a stronger compression function. And Maritime has done great work on, you should read his latest papers on block cipher research. There's quite some progress here, how to build a hash function based on a block cipher. On permutation, there is also very nice work. For example, it's shown that if you go from 2n bit to n bit, you need at least 3 permutations. There has been very nice work, and the most recent thing I want to advertise for my student who classified all the functions that use 3 permutations and 3 XORs, and he found out that there is up to equivalence 48 functions which actually have collision and per-image security. So there is quite some new insights. On the other hand, it's still a very hard thing. I can go on the board and draw a few permutations and a few lines and XORs, and then the student works for several months to understand what the properties are. Right? This is more or less the game. So we made quite some progress because I think 5 years ago it would be very hard to say anything about these structures. We have good tools as well. But of course, as soon as I add a few more layers, we are lost completely. So the tools will say something, but I don't think we can now prove anything. And of course, we still need to assume that those building blocks are ideal or random ideal permutations, ideal block ciphers. And anyway, should we be doing this? Because it's been historically a very important game to build everything based on AES or DES historically. But I mean, Johan's Damen view is, why deal with all this old crypto? I make a permutation on 1600 bits. And then you don't need all these kind of reductions to 3 permutations. I just make one big one and go to hell with your proof. That's essentially what he says, right? I mean, so the question is, where do you shift the difficulty? Because now he has to convince you that this big permutation is ideal. So, and then I think a very interesting problem is, what if the building block is not ideal? Because you see in the SHA-3 competition quite some results, at least for reduced round versions, say 30% of the rounds or 50% of the rounds, you can show some non-ideal properties. And it's still a very big debate which ones are relevant. But essentially, what would be very nice is that you can say if the non-ideal property is within certain bounds or certain statistical deviations or whatever, you can still prove security. And there have been some results, I think the Chabal team, a weakness was found in Chabal building block, and they could actually make one of their proofs work still, in spite of the weakness. So that may be a very interesting topic for further research. But whether SHA-3 will be a sponge or Merkle-Damgard, so the large permutation, or do things the same as before but more or less double state, or something in between, a hybrid, is still completely unclear. There is no clear view what in theory should be the best. So move on to real life. So historically everything was done based on block ciphers. And of course we have the very big change around 1990 from hardware to software, and today we look at schemes based on permutations. It's very slow schemes, but we start to understand them better. In the late 80s, early 90s, there were quite some schemes which are number theoretically secure based on discrete log or factoring, but they're very, very slow. And the ones that are fast actually don't really have all the properties you want. They only give you one property. And then, of course, around 1990, Rivest and Merkle, those two again, started making fast software hash functions, and with some bad consequences. There is now a second generation, and so SHA-3 is actually where we hope to be. So this is an important slide, I think, for practitioners. So pre-2001, DES is 50 cycles per byte, triple DES is 115, MD4 and MD5 is 3 to 5 cycles per byte. Today, SHA-2, depending on the machine, it goes down to 10, 20. They get faster and faster, especially on 64-bit machines. This one gets very fast. But AES is 5 to 10 cycles per byte. AES-based hash functions are much slower. So the world has changed. When the Internet protocols were done, hashing was fast, block ciphers were slow. The world is changed. Hash functions are slow, block ciphers are fast. And so we have to rethink all our protocols, but this is very difficult, right? Legacy, and you heard all the stories from the people from industry. But if you do something new, try to remember this. So here is the hash function crisis in one graph. And so people always claim that actually the crisis started in 2004. But really the crisis started in this room, actually, 1996, when my late friend Hans Dobbertin, who gave a talk here on showing how to break MD6 to the 20 steps. That's really when the crisis started. And of course, one Abbott's very nice techniques, but in fact the crisis was very clearly happening already from 96. So you've heard the story, so I can be fast. Very quickly, the recommendation was stop using MD5 because also problems for MD5 were found by Hans Dobbertin on compression function. But even a few years ago, you click on any certificate and find MD5, until of course this attack happened. Very cool attack where people actually asked for a user certificate and found a CA certificate in their mailbox as a present using collisions. So, and I think as it kept amazing me even after having so much experience in industry that actually in 2008 there were still so many CAs using MD5. Obviously for legacy purposes, because nobody wanted to change the applications, but still it's kind of shocking. It was predicted it would happen more or less. People were speculating it wouldn't happen. SHA-1 I think has been the big failure of the research community because we've actually found collisions in a verified paper in 2069. And since then there have been at least 6 announcements of better results, but as far as I know none of the attacks works or is published, or when they try to implement it they have problems, but they don't tell each other because everybody wants to be famous, be the first person finding collisions for SHA-1. So there is no collaboration and they all get stuck. And anyway, they also are working on SHA-3. So my prediction is this fall, all these people will start working again on this problem. So as Christmas present, we may get a collision for SHA-1. But I'm very embarrassed because I keep showing this slide already for 4 years. And NIST actually said you can use SHA-1 fine until 2010. So in fact, we kind of lost against NIST, right? We should really have found collisions before 2010. So I guess that's the message here, right? Or you can also have this message on the Golden Gate Bridge. So Should we jump from the bridge or not? Should we still look at theory or not? So SHA-3 tries to be the crisis solver. So big open competition, 64 submissions. This is a warning. Every time you do competition, this doubles. So the next people who do competition, then authenticated encryption, you may get 128 submissions. That's my prediction. So very quickly, I think in 9 months, about 30 were broken. Of those 64, 14 were selected. Then December 2010, 5. And so nobody knows when NIST will decide, whether it will be before the summer holiday or after the summer holiday. But last time, they announced the decision for AES in September or October. But of course, the presidential elections may interfere with this and so on. We don't know. But I think it will be after the summer. That's my prediction. They have a lot of material to chew on. These are just funny slides to entertain you and keep you awake. Done by the Cañera, which where all the submissions came from. I guess many of you have seen them, but it's really nice. So this is the attacks. I really love this one. So especially if you go to the US and you show that all the cryptanalysis is being done in Europe, because all the arrows start from Europe and go to the US and Asia. And then what's left standing was this. Not much in Asia and the US, and then the round 2 candidates. So the biggest winner there was France. And then the finalist, the bigger loser, was France, because there was no French algorithm. This must be the consequence of this French fries and freedom fries. So this is the latest revenge for this. So anyway, which one to pick? It's very difficult, and I'm being recorded here, so I'm not going to say much, because I have too many friends in the community to lose. You can talk to me offline afterwards. So this is a very nice graph done by Dai Watanabe, which actually shows diversity. So ARX is addition rotated XOR, which is SHA-1, SHA-2, MD4, MD5, and so on. So Blake and Skane use this approach. Gröstel uses 8-bit S-box. This is the AES corner of the world. And GH and Ketchak are the brave ones. They use small S-box. It's a different, maybe you can say the Serpent approach, small S-box. 3-bit, 4-bit. The ones on the inner circle have a small state, although Skane has both a small state and a large state. If you measure performance, you use a small state. If you measure security, you use a large state. This is how you should win a competition. There's several people who have found out this trick. It's very clever. And so you see Ketchak as the largest state, GH and Gröstel are intermediate. So this was a state of security reductions, and I'm not going to explain to you what this is. But this is the hard work. Mostly in our team we did, but of course several results are done by others and they've been incorporated. This is for the 14 second round candidates, which properties we can prove for the hash function and for the compression function. Of course, for some you can't prove things because like Ketchak doesn't want a secure compression function, so there is no security here. But what is amazing is there is a lot of white things, which means we don't know the answer, or yellow things, which means weak reductions. So we worked more on this, and so this is the latest update. So you see here the reductions for the 5 finalists. It made it slightly easier. We put security levels rather than these O notations. So you see that Ketchak and Skane actually have better indifferentiability bound than the others. And then some more recent work is that Blake actually had a security proof assuming the compression function was ideal, but then we showed it's not ideal. But then a new proof is written taking into account the properties of the compression function, we could show anyway the bounds. So kind of the thing could be saved. But security is based on the iteration now for Blake. And so also for GH we did some improvements because we could not use those, we could not fill those columns based on the 170 in this column, so the infinitability bound for GH is a bit weaker, so it's not good enough. You have to make dedicated proofs to get there. So 5-tailed bit, so you see GH is slightly problematic because the bounds are not as good. So you see Gröstel is the only one who doesn't protect against long messages, but it's a deliberate decision. And you see GH in terms of indifferentiability looks slightly weaker. What I find actually amazing is that there is only a handful of people working on these problems. There's a little bit of people, I would say a few teams, 5, 10, 15, 20 people working on cryptanalysis, but this is 2 or 3 or 4 people who are interested in what is the soundness of this structure? I mean, with the given reduction proofs, what can I prove given assumptions on the building block? What can I prove about the hash functions? So, and also it seems that these results fall in between 2 chairs. I think you see this is not relevant because it's a particular construction. We don't find this interesting. And the cryptanalysts say it's not cryptanalysis. So this is kind of a difficult field to publish things. And so I think there's quite some progress being made. I don't think you would have been capable of filling those gaps with what was known 5 years ago. A lot of work has been done to improve this. So can we, of course, all these proofs use a lot of ideal assumptions. There is some infinity bounds that have to be improved still, and so for GH I showed you these yellow things. We probably think we can improve those. So to wrap up, what about real proofs? Because I went quite quickly, but you saw there were 2 designs, or maybe 3. There was also an ECC-based design submitted with a proof of the compression function based reduction to a hard problem. But then all these 2 problems, they're based on lattices or knapsacks or whatever. And there's actually quite nice research showing that, for example, if you have a knapsack, you have a woof and so on, all these nice properties. But as an engineer, if I look at a hash function based on adding vectors, it's linear, guys. It's linear. You may prove nice things, but if you look at it, it's linear. And so you may not be able to find collisions, but there's going to be weird structural properties popping up. That's the problem. The Swift people had a very nice, efficient design, but they realized that they needed something more, so they made a sandwich with additions, then S boxes, then additions. But I mean, that starts looking like an engineering design, right? I mean, because how do you choose the S boxes then? And also, the whole thing was rather slow, 57 cycles per byte. Another design was based on coding theory and had reductions. But then, of course, the problem is you end up with a large value at the end, and as output transformation, they chose whirlpool. But if you choose whirlpool already, you have to implement whirlpool. Why do you still want to implement this, right? I mean, it's kind of, I can see the argument if the cost is not an issue, but I can also see it was very hard for them to win the competition. So their speed was 324, but Tanya and Dan have now a similar construction which goes at 10 cycles per byte, and you can talk to them if you want to find out how it works. So you can get speed, but I guess they still need whirlpool at the end to be secure, or they can argue with us about that. Okay, so time to wrap up. So we've seen a cryptographic meltdown for sure, but fortunately we don't sign documents, and we actually, in spite of all our claims, we don't need collision resistant all that much, right? Although I think I can imagine a scenario with code signing where somebody gets his device driver by Microsoft approved and then actually produce malware which has the same hash value. So you could see clever attacks there. And of course the attack on the CA is very pretty and has implications. So if you want to design a hash function, the half-life of your function is about 1 year. So I tell my PhD students, design the hash function right before you defend, not 1 year in advance, right? Or do cryptanalysis, because it's very risky business to be there. I do think that theory has made progress. I mean, I've made fun of something, but on the other hand, there is now quite some results, quite some insight. There is also many open problems. I think we now understand better what we don't understand. There is also many things we now understand better. But if I would have to draw the bridge or picture, I would say this. It's like partly foggy, but we at least see a little bit how we can go from theory to practice. But of course, what we really would like to have is efficient hash functions with security reductions. But we're still quite far from that. Thank you very much for your attention.
We have time for a few quick questions.
Just a very small point. You mentioned that the idea of randomizing hash functions, I can't remember now who you attributed it to, but of course the idea is essentially due to Donald Davis, I think.
Yes, it's already in some of his papers,
yes,
for sure. I mean, it's popped up several times, but it's true that Donald Davis was one of the first ones in one of his old reports. That's for sure. But it doesn't happen in practice, right? I mean,
no.
Very few people sign things, and if they sign, they don't randomize. At least I have not seen many applications where it's being done.
So, like an open-ended question, like we've seen like talks and many results recently in analyzing network protocols with formal method tools like SAT solvers. And there were like a couple of years ago, there were like some papers trying to apply some of these ideas to the design of hash functions. It was paper by Miron, and there were like maybe some follow-up, but after that there was nothing seems to happen. And I'm not sure if any of those papers you mentioned utilize any of these techniques. So is there any room for formal methods people to apply anything or add something?
Yeah, I see two elements in your question. I mean, the formal methods. I mean, I know that I think it's so Timer, you want a tool to analyze all these functions, right? I mean, once you start analyzing these permutations, I think you can, in any way, if it hasn't been done, you can imagine that, you know, especially those schemes with block ciphers or permutations, and you write a tool that starts classifying them. And for example, to do the pre-permutation scheme, I know my student wrote a tool, so you could actually teach it attacks, so you can find out which schemes are insecure or secure, and then try for the secure ones to automate a proof. That could actually bring you further. But I think security proofs for the iteration are much harder if the building block is weak. But maybe, I think it can be automated. But again, I think the deeper question is, do you want to keep working on these small building blocks to big ones, or do you want to design big building blocks? Now, on the use of set solvers in cryptanalysis, so if you look at the techniques used by Doherty in MD4, and also by Wang on MD4 and MD5, so it's essentially solving Boolean equations in a clever way where you force certain values. Right. And so I think, and also for block ciphers, so I think there has been some evidence that in some cases these tools can help you. But the real problem is it's a black box, right? I mean, you put your problem in there, you get an answer or you get no answer. And if after 1 week you get no answer, what do you do? So that's, I think there could probably be more progress made if cryptanalysts would learn how these equations are solved and use those techniques to break things. Yeah. Because applying those things in black box, well, if you make a very small block cipher, you can probably break it with the set solver, you can also break it by hand. And there may be a gray zone where you can make progress, but to really have impact, I think cryptanalysts should learn how these set solves work and use the same heuristics and apply them to their problems.
I'm wondering, do you see any applications where you would use provably secure, collision-free or collision-resistant hash functions? Like somewhere where we could simply abolish these kinds of hash functions to start with, and then don't worry about it for the next couple of years.
Yes, well, any application that wants to go to court in Australia obviously needs that, right? I mean, that's the least requirement you have there in Australia. It's a good question. So, because hash functions are put everywhere, there is this enormous performance thing, right? I mean, so, because it's in HMAC, it's in every packet of the internet is MAC'd, and so if your hash function is slow, it will not be accepted. But I think there is many cases where you don't care as much. It may be code signing for embedded devices. Because anyway, you have to sign. So you have to do an RSA operation anyway. So even if the hash function, okay, it's of course on a larger data. So I think there is definitely applications also where humans sign, right? I mean, if you really sign as a human in a deliberate way, you don't sign 500 documents a day, right? So there the speed actually is not so important, and you could use some of those democratic constructions. So I think there is some cases where you could use them.
So going back to this morning's talk, so it was mentioned this debate Ian Veer having about choosing ECDSA versus EC Schnorr, and one of the benefits of using EC Schnorr is that you're not reliant on the collision resistance of the hash
because
function.
you hash the random together.
Because you hash the random commitment in, so it's only signature schemes which are old-fashioned in sense of hash and sign are the problem.
Yes, for sure. Again, of course, unless you have a signer attack, which you have then to look in EMV whether it's a problem or not.
Yeah.
Right? It's
Thanks.
very much.